Hello everyone, I'm Professor Chia-Po Wei. Course information such as exam results or the solution of the weekly quiz will be posted both on the announcement board of Cyber University and on our course website. We will still use remote teaching, and the weekly quiz starts from Monday 8:30 a.m. and the solution of the weekly quiz will be posted on Wednesday. If you have any questions about the course contents, you can contact me or you can contact the teaching assistants using the TA hours. In this week, we are going to study section 5.2, Orthogonal Subspaces. In this section, we will consider four subspaces, that is, the column space of A, the null space of A, the column space of A transpose, and the null space of A transpose. The four subspaces are defined in section 3.6, and the four subspaces are called the fundamental subspaces of a matrix A. In section 5.2, we are going to study the relationship among the fundamental subspaces, and we will give the definition of orthogonal subspaces. In particular, we will prove the null space of A transpose is the orthogonal complement of the column space of A, and the null space of A is the orthogonal complement of the column space of A transpose. First, we will revisit the definition of the column space of A. Let A be a matrix of dimension m times n. Then the column space or the range space of A is denoted by Ra. Here, R stands for range. Ra is the subspace of Rm, spanned by the column vectors of A. Or we can say Ra is the collection of all linear combinations of column vectors of A. We can use the mathematical language to give a precise definition of Ra. Ra is the set of vectors B in Rm, such that B can be written as Ax for some x in Rn. We know that Ax is Ax equals x1a1 plus x2a2 plus up to xn which is a linear combination of column vectors of A, and x1, x2 up to xn are the coefficients of the linear combination. So B equals Ax means B can be written as a linear combination of column vectors of A for some x in Rn, and x is the coefficients of the linear combination. Given a matrix A of dimension m times n, then we can define a linear transformation L of x as Ax. Then L is a mapping from Rn to Rm. And we know that the column space of A is a subspace in Rm because each column vector of A is in Rm, and the range space of A is the image of Rn under the linear transformation L. And we also revisit the definition of the null space of A. The null space of A is the collection of all vectors in Rn, such that Ax equals the zero vector in Rm, and thus every vector in Na in the null space of A will be mapped to the zero vector in Rm. And we know that both the null space of A and the column space of A are subspaces, and therefore the null space of A will contain the zero vector in Rn, and the column space of A will contain the zero vector in Rm. In this slide, we revisit the definition of the row space of A and the column space of A transpose. The row space of A is the subspace of R1 times n, which is spanned by the row vectors of A. Because each row of matrix A corresponds to a column of A transpose, so next we consider the column space of A transpose, which is the collection of all vectors D in Rn, such that D equals A transpose Y for some Y in Rm. And we know that A transpose Y equals Y1 R1 plus Y2 R2 plus up to Ym Rm. Here, R1, R2 up to Rm are column vectors of A transpose, and Y1, Y2 up to Ym are the coefficients of the linear combination. And we know that if R1 is a column vector, if R1 is the first column vector of A transpose, then R1 transpose will be the first row of matrix A. And similarly, if Rm is the nth column vector of A transpose, then Rm transpose will be the nth row of matrix A. And we know that the column space of A transpose lies in Rn, and the row space of matrix A lies in R1 times n. Next, we use the figure in this slide to revisit the definition of the range space and the null space of A transpose. Give a matrix of dimension m times n, then we define a linear transformation L star of x as A transpose S times x. Then L star is a mapping from Rm to Rn, and we know that the range space of A transpose lies in Rn because each column vector of A transpose lies in Rn, and the range space of A transpose is the image of Rm under the linear transformation L star. We also revisit the definition of the null space of A transpose, which is the collection of vectors in Rm such that A transpose X equals the zero vector in Rn, and therefore every element in the null space of A transpose will be mapped to the zero vector in Rn. And note that both the null space of A transpose and the range space of A transpose are subspaces, and so the null space of A transpose contains the zero vector in Rm, and the column space of A transpose contain the zero vector in Rn. In this slide, I will summarize the main results of section 3.6 and section 5.2. And we recall the four fundamental subspaces of matrix A is the range space and the null space of A, and the range space and the null spaces of A transpose. We know that both the column space of A and the null space of A transpose are in Rm, while the null space of A and the column space of A transpose are both in Rn. And recall that rank A is the dimension of the row space of A, which also equals the dimension of the column space of A. And the nullity of A is the dimension of the null space of A. The rank nullity theorem in section 3.6 states that rank A plus nullity A equals n, where n is the number of column vectors. We also have rank A equals rank A transpose, which means the dimension of the row space equals the dimension of the column space. And in section 5.2, we will prove the fundamental subspaces theorem, which relates the null space with the column space of A transpose, and relates the null space of A transpose with the column space of A. And we will also prove Rn is the direct sum of the null space of A and the column space of A transpose, and Rm is the direct sum of the null space of A transpose and the column space of A. Later, we will give detailed proofs of the two of these theorems. Next, we give the definition of orthogonal subspaces. Two subspaces X and Y in Rn are said to be orthogonal if X transpose Y equals 0 for every X in X and for every Y in Y. If X and Y are orthogonal, then we write X perp Y, where the symbol perp means perpendicular. We use example 1 to illustrate orthogonal subspaces. Let X be span of E1, which is the x-axis in R3, and Y be the span of E2, which is the y-axis in R3. If X belongs to the x-axis and Y belongs to the y-axis, then X can be expressed as x1 0 0, and Y can be expressed as 0 y2 0, and thus X transpose Y always equals 0 for any scalars x1 and y2, and therefore we know X and Y are orthogonal subspaces. And we use the notation X perp Y to mean X and Y are orthogonal subspaces. The next example, we let X be span of E1 and E2, so X is the xy plane, and let Y be the span of E2 and E3, and Y is the yz plane in R3. If X belongs to the xy plane, then the vector x can be written as x1, x2, 0. And if y belongs to the yz plane, then y can be expressed as 0, y2, y3, where x1, x2, y2, y3 are arbitrary scalars. And we know the scalar product x transpose y equals x2, y2. And if x2 and y2 are not zeros, then we know x transpose y is not equal to 0. And hence, we can always find some x in the x plane, in the xy plane, and some y in the yz plane, such that x transpose y is not equal to 0, and therefore x and y are not orthogonal subspaces. Next, we give the definition of orthogonal complement. Let Y be a subspace of Rn, and the set of all vectors in Rn that are orthogonal to every vector in Y will be denoted by Y perp. That is, Y perp is the set of all vectors in Rn such that x transpose Y equals 0 for every y in the subspace Y, and the set Y perp is called the orthogonal complement of Y. We will use example 2 to illustrate orthogonal complement. Let X be the span of E1, E2, which is the xy plane in R3, and let Y be the span of E3, which is the z-axis in R3. If X belongs to the xy plane, then X can be written as x1, x2, 0, where x1 and x2 are arbitrary scalars. If Y belongs to the z-axis, then Y can be written as 0, 0, y3, where y3 is an arbitrary scalar. Then we know x transpose y. Then we know x transpose y always equals 0 for arbitrary scalars x1, x2, and y3, and therefore x and y are orthogonal subspaces. In fact, x equals y perp because the element in X is orthogonal to every vector in Y. And we also have Y equals X perp because every element in Y is orthogonal to every vector in X. You can verify this by yourself. Next, we revisit example 1. In example 1, we let X be the x-axis and Y be the y-axis in R3. X and Y are orthogonal, but they are not orthogonal complements because X perp equals the span of E2 and E3, which is the YZ plane, and Y is only a subset of X perp. Similarly, Y perp is the span of E1 and E3, so Y perp is the XZ plane in R3, and we know that X is only a subset of Y perp. In this slide, we present two remarks on orthogonal subspaces. First, if X and Y are orthogonal subspaces of Rn, then the intersection of X and Y equals the set of the zero vector. Suppose X is in the intersection of X and Y, and x and y are orthogonal subspaces, then the scalar product of x and itself equals 0 because x and y are orthogonal subspaces. Due to the first property in the definition of the inner product, we know x must be the zero vector, and hence the intersection of x and y contains only one vector, that is the zero vector. The second remark is that if Y is a subspace of Rn, then Y perp is also a subspace of Rn. To prove this, we need to show the scalar multiplication is closed in Y perp, and we also need to show the vector addition is also closed in Y perp. To this end, we consider x in Y perp, and we want to show alpha x is also in Y perp, and we compute the scalar product of alpha x and y, which equals alpha times the scalar product of x transpose of x and y. Because x belongs to Y perp, so x transpose y equals 0, and hence alpha times 0 is also equal to 0, and therefore alpha x belongs to Y perp, so the scalar multiplication is closed in Y perp. Next, we want to show if x1 and x2 are in Y perp, then x1 plus x2 is also in Y perp. Then we compute the scalar product of x1 plus x2 and y, which equals x1 transpose y plus x2 transpose y. Because x1 and x2 are elements of Y perp, so x1 transpose y equals 0, and x2 transpose y also equals 0, and therefore x1 plus x2 transpose y is 0. Hence we know x1 plus x2 belongs to Y perp, and therefore the vector addition is also closed in Y perp. In this slide, we discuss the relationship among the following three conditions. The first condition is x and y are orthogonal subspaces. The second condition is that x is a subset of Y perp. And the third condition is that y is a subset of x perp. What is the relationship among the three conditions? In fact, the three conditions are all equivalent. To show this, I depict two figures in this slide. The right-hand side figure depicts the relationship between condition 1 and condition 2. If x and y are orthogonal subspaces, then x is a subset of Y perp. Because Y perp is the set of all vectors that are orthogonal to every vectors in Y. And the left-hand side figure depicts the relation between condition 1 and condition 3. If x and y are orthogonal subspaces, then y is a subset of x perp, because X perp is the set of all vectors that are orthogonal to every vector in X. In this slide, we prove the fundamental subspaces theorem. If A is a matrix of dimension m times n, then the null space of A equals the orthogonal complement of the column space of A transpose. And we also have the null space of A transpose equals the orthogonal complement of the column space of A. We only prove the first equality, because if the first equality is true, then we can replace A with A transpose and obtain the second equality. To prove the first equality, we need to show two inclusions. The first inclusion is the null space of A is a subset of the orthogonal complement of the range space of A transpose. The second inclusion is the orthogonal complement of the column space of A transpose is a subspace of the null space of A. If the two inclusions are both true, then this means the null space of A equals the orthogonal of the column space of A transpose. First, we prove null space of A is a subset of the orthogonal complement of Ra transpose. To do this, we need to show if X belongs to the null space of A, then X also belongs to the orthogonal complement of Ra transpose. If X belongs to the null space of A, then we have Ax equals the zero vector. Then we take transpose on both sides and obtain X transpose times A transpose equals the zero vector. In view of this equality, then we know X transpose A transpose Z equals 0 for all Z in Rm. Then we denote A transpose Z as Y. Then we have X transpose Y equals 0 for all Y in the column space of A transpose. Because if Y equals A transpose Z, then Y is a linear combination of column vectors of A transpose. Hence, Y is in the column space of A transpose. Then, by definition of orthogonal complement, then we know X belongs to the orthogonal complement of the column space of A transpose. Next, we prove the orthogonal complement of Ra transpose is a subset of the null space of A. To do this, we need to show if X belongs to the orthogonal complement of Ra transpose, then X also belongs to the null space of A. Suppose X belongs to the orthogonal complement of Ra transpose, then by definition of the orthogonal complement, we know X transpose Y equals 0 for all Y in the column space of A transpose, which means X transpose Ri equals 0. Here, Ri is the ith column of A transpose for I from 1 to up to m. If we take transpose of the right hand side and the left hand side, we obtained Ri transpose X equals 0 for I from 1 to up to m. And if we stack the equalities vertically, then we obtain R1 transpose X, R2 transpose X, up to Rm transpose X equals the zero vector. And we know that because Ri is the ith column of A transpose, so Ri transpose is the ith row of matrix A. Therefore, R1 transpose, R2 transpose up to Rm transpose is actually the matrix A. So now we have Ax equals the zero vector, and hence X belongs to the null space of A, and the proof is finished. One important consequence of the fundamental subspaces theorem is that because the null space of A is the orthogonal complement of the column space of A transpose, so the null space of A and the column space of A transpose are orthogonal subspaces. Then, in view of the previous remark, we know the intersection of the null space of A and the column space of A transpose contains only the zero vector. Similarly, we know that because the null space of A transpose and the column space of A are orthogonal subspaces, and therefore their intersection only contains the zero vector. In this slide, we will prove Theorem 5.2.2. This theorem has two statements. The first statement is that if S is a subspace of Rn, then dimension of S plus the dimension of S perp equals n. The second statement is that if x1, x2 up to xr is a basis for S, and xr plus 1, xr plus 2 up to xn is a basis for S perp, then the union of the two bases is a basis for Rn. First, we will prove the first statement. If S is not equal to the set containing only the zero vector, and we let x1, x2 up to xr be a basis for S, and we define S to be a matrix of dimension R times n, whose ith row is Si transpose for each I. Then we will have the rank of X equals R, because x1, x2 up to xr are linearly independent. And we also have the column space of X transpose equals S, because the ith column of X transpose is Xi. Si is the ith element in the basis for S. So the column space of X transpose equals S. Now we can compute S perp. Since S equals the column space of X transpose, so S perp equals the orthogonal complement of the column space of X transpose. Then, by the fundamental subspaces theorem, we know the orthogonal complement of Rx transpose equals the null space of X. Now we can compute the dimension of S plus the dimension of S perp, which equals the dimension of Rx transpose plus the dimension of the null space of X. Because the dimension of Rx transpose is the rank of X transpose, and the dimension of the null space of X is the nullity of X. So we have the second equality. And from the result in section 3.6, we know rank X transpose equals the rank of X. Hence, we have the third equality. And we know from the rank nullity theorem, rank X plus the nullity of X equals n. N is the number of columns in X. And thus, we have proved the first statement of Theorem 5.2.2. Next, we prove the second statement. If x1, x2 up to xr is a basis for S, and xr plus 1, xr plus 2 up to xn is a basis for S perp, then the union of the two bases is a basis for Rn. It suffices to show that the n vectors are linearly independent, because the dimension of Rn is n, and thus if the n vectors are linearly independent, then the n vectors can span Rn. To prove that the n vectors are linearly independent, we consider C1x1 plus C2x2 plus up to Cn equals the zero vector. And we want to solve this equation where C1, C2 up to Cn are the variables. If the only solution to this equation is C1, C2 up to Cn are all zeros, then we can say x1, x2 up to xn are linearly independent. To this end, we denote y as C1 x1 plus up to CR xr, and denote z as CR plus 1 xr plus 1 plus up to Cn xn. Then we have y plus z equals the zero vector, or equivalently y equals negative z. We know that y is in S because y is a linear combination of elements in the basis for S, and z is in S perp because z is a linear combination of elements in the basis for S perp. And because y equals negative z, so we know y is also in S perp. Similarly, z can be written as z equals negative y, so z is also in S. And therefore we know both y and z are in the intersection of S and S perp. And recall that S and S perp are orthogonal subspaces. So the intersection of S and S perp is the set containing only the zero vector. Therefore, both y and z are the zero vector. And because y is the zero vector, we have the first equality, and z also equals the zero vector, so we have the second equality. And recall that because x1, x2 up to xr is a basis, so x1, x2 up to xr are linearly independent, and therefore the first equality implies that C1, C2 up to CR all equal 0. Similarly, because XR plus 1 up to XN is a basis, so XR plus 1 up to XN are linearly independent. And the second equality, CR plus 1, XR plus 1 plus up to Cn xn equals 0, implies that CR plus 1, CR plus 2 up to Cn all equal 0. And therefore, the only solution to the first equation is C1, C2 up to Cn all equal 0. And therefore, x1, x2 up to xn are linearly independent. So x1, x2 up to xn is a basis for Rn, and the proof is finished. Next, we give the definition of the direct sum. If U and V are subspaces of a vector space W, and for each W in vector space W, and W can be written uniquely as the sum of U plus V, where U is from subspace U and V is from subspace V, then we say W is a direct sum of U and V, and we use this notation to denote W is a direct sum of U and V. If W is a direct sum of U and V, then every vector in W can be written uniquely as a sum of two parts, where the first part is from the first subspace and the second part is from the second subspace. Next, we introduce Theorem 5.2.3. If S is a subspace of Rn, then Rn is a direct sum of S and S perp. We can use a simple example to gain some insights behind Theorem 5.2.3. Suppose S is the x-axis in R3, then S perp is the YZ plane in R3. Clearly, R3 is the direct sum of the x-axis and the YZ plane. Next, we prove Theorem 5.2.3. Suppose the dimension of S is R, where R is greater than 0 and R is less than n. If R equals 0 or R equals n, then the proof is trivial. Suppose x1, x2 up to xr is a basis for S, and the xr plus 1 up to xn is a basis for S perp. Then from Theorem 5.2.2 we know the union of the two bases is a basis for Rn, and therefore each x in Rn can be written as a linear combination of x1, x2 up to xn. Then we denote U as C1x1 plus C2x2 plus up to CRxr, and denote V as CR plus 1 XR plus 1 plus up to CNxn. Then U belongs to S because U is a linear combination of x1, x2 up to xr. And V belongs to S perp because V is a linear combination of xr plus 1, xr plus 2 up to xn. And now we have x equals U plus V. Therefore, for every x in Rn, we can always express x as the sum of two parts, where the first part is from S and the second part is from S perp. To complete the proof, we need to show uniqueness. To this end, we suppose x also equals y plus z, where y belongs to S and z belongs to S perp. If we can show y equals u and z equals v, then the uniqueness is proved. To this end, we consider we consider x equals u plus v equals y plus z. After some arrangements, we have u minus y equals z minus v, and we know that u minus y belongs to S because S is a subspace, and the vector addition is closed in S. Similarly, z minus v belongs to S perp. Because S perp is also a subspace, so vector addition is closed, and z minus v belongs to S perp. We know that u minus y belongs to S, and z minus v belongs to S perp, and we also have u minus y equals z minus v, so u minus y also belongs to S perp, and z minus v also belongs to S, and therefore both u minus y and z minus v is in the intersection of S and S perp. However, the intersection of S and S perp is the set containing the zero vector. Therefore, both u minus y and z minus v are the zero vector. Hence, we have u equals v and v equals z, and therefore the uniqueness is proved. And we have shown every x in Rn can be uniquely expressed as the sum of two parts, where the first part is from S and the second part is from S perp, and therefore the proof is finished. Next, we prove Theorem 5.2.4. If S is a subspace of Rn, then the perp of S perp equals S. We can use a simple example to gain some insights behind this theorem. Suppose S is the x-axis in R3, then the S perp will be the YZ plane in R3, and the perp of the YZ plane is the x-axis. Hence, the perp of x-axis equals the x-axis. Next, we prove Theorem 5.2.4. We need to show the two sets are equal. To this end, we need to prove two inclusions. The first inclusion is S is a subset of the perp of S perp. The second inclusion is the perp of S perp is a subset of S. If the two inclusions can be proved, then we can say the two sets are equal. We prove the first inclusion. If X belongs to S, and if we can prove X also belongs to the perp of S perp, then we can say S is a subset of the perp of S perp. If S belongs to S, then X transpose Y equals 0 for every Y in S perp, because S and S perp are orthogonal subspaces. So we have X transpose Y equals 0 for every Y in S perp. However, this is the definition of the perp of S perp. In view of the definition of the perp of S perp, we know X belongs to the perp of S perp, and hence the first inclusion is proved. Next, we prove the second inclusion. Consider X belongs to the perp of S perp, and if we can show Z also belongs to S, then we can say the perp of S perp is a subset of S. If Z belongs to the perp of S perp, according to Theorem 5.2.3, Z can be uniquely expressed as the sum of U and V, where U belongs to S and V belongs to S perp. Know that Z belongs to the perp of S perp, and V belongs to S perp. Hence, Z and V are orthogonal, and therefore V transpose Z equals 0. Then we substitute Z equals U plus V. Then we obtain V transpose U plus V transpose V equals 0. Because V and U are orthogonal, because S and S perp are orthogonal subspaces, so V transpose U equals 0, and therefore we obtain V transpose V equals 0. Recall that the inner product of a vector and itself, if equals 0, then this vector must be the 0 vector. Hence, V is the 0 vector. Then we know Z equals U plus V equals U, and U belongs to S. Hence, Z must belong to S, and therefore the second inclusion is proved. In view of Theorem 5.2.4, we have the following remark. Recall that by the Fundamental Subspaces theorem, we have the null space of A equals the perp of the column space of A transpose, and the null space of A transpose equals the perp of the column space of A. Then by Theorem 5.2.4, if we take perp on both sides, then we obtain the perp of the null space of A equals the column space of A transpose, because the perp of RA transpose equals RA transpose. And if we take and similarly we obtained the perp of the null space of A transpose equals the column space of A, because the perp of RA equals RA. From this equality, we know the null space of A is the orthogonal complement of RA transpose, and from this equality, we know RA transpose is the orthogonal complement of the null space of A. Hence, the null space of A and the column space of A transpose are orthogonal complements of each other. Similarly, the null space of A transpose and the column space of A are orthogonal complements of each other. Next, we prove Corollary 5.2.5. If A is an m times n matrix and B is a vector in Rm, then either layer is a vector x hat in Rn such that ax hat equals b, or layer is a vector y in Rm such that a transpose y equals the zero vector and the y transpose b is not equal to 0. To prove this corollary, know that given a vector b in Rm, the linear system Ax equals b is either consistent or not consistent. If it is consistent, then b is in the column space of A, then there exists S hat in Rn such that Ax hat equals b. On the other hand, if the linear system is not consistent, then B is not in the column space of A. Recall that Rm is the direct sum of the column space of A and the perp of the column space of A. By the Fundamental Subspaces Theorem, we know the perp of the column space of A is the null space of A transpose. So Rm is the direct sum of the column space of A and the null space of A transpose. By definition of the direct sum, every vector b in Rm can be written as the sum of z and y, where z belongs to the column space of A and y belongs to the null space of A transpose. Because B is not in the column space of A, and we have y is not the zero vector. And clearly, the vector y satisfies the following two conditions. The first condition, A transpose y equals the zero vector, means y is in the null space of A transpose. The second condition, y transpose b, is not equal to 0, because y transpose b equals y transpose z plus y transpose y. Y transpose z is 0, and y transpose y is greater than 0 because y is not the zero vector, and the proof is finished. In this slide, we will prove the final remark in this section. Given a matrix A of dimension m times n, then we can define a linear transformation L of x as Ax. Then L is a mapping from Rn to Rm. If we restrict the domain from Rn to Ra transpose, and restrict the codomain from Rm to Ra, then the linear transformation L is invertible. Invertible means 1 to 1 and onto. First, we prove L is onto. To show L is onto, we need to show for every vector b in Ra, we can always find some vector y in Ra transpose such that Ay equals b in Ra. Recall that Rn is the direct sum of the null space of A and the perp of the null space of A. By the Fundamental Subspaces Theorem, the perp of the null space of A equals the column space of A transpose, and hence Rn is the direct sum of the null space of A and the column space of A transpose. By the definition of the direct sum, every vector x in Rn can be written as the sum of y and z, where y belongs to the column space of A transpose and z belongs to the null space of A. Now we compute Ax, which equals Ay plus Az. Because z belongs to the null space of A and Az equals 0, hence Ax equals Ay. And recall that the column space of A is the collection of all linear combinations of column vectors of A, and can be written as the set of Ax, where x is arbitrary vector in Rn. And in view of the relation Ax equals Ay, we know the column space of A can also be written as the set of Ay, where y is arbitrary vector in the column space of A transpose. Thus, if we restrict the domain of L to Ra transpose, then L maps Ra transpose onto Ra. Next, we prove L is 1 to 1. To show L is 1 to 1, we need to prove if Ax1 equals Ax2, then x1 must be equal to x2. Consider x1, x2 in the column space of A transpose, and suppose Ax1 equals Ax2. Note that we only need to consider x1, x2 in the column space of A transpose because we have restricted the domain to Ra transpose. Then we have A times parentheses x1 minus x2 equals the 0 vector, which means x1 minus x2 belongs to the null space of A. And we know that because x1, x2 belong to the column space of A transpose, hence x1 minus x2 also belong to the column space of A transpose, because Ra transpose is a subspace, and the vector addition is closed in a subspace. So x1 minus x2 is in the intersection of the null space of A and the column space of A transpose. Because the null space of A and Ra transpose are orthogonal subspaces, their intersection is the set containing only the 0 vector. Hence, x1 minus x2 must be equal to the 0 vector, and hence x1 equals x2, and L is a 1 to 1 function, and the proof of this remark is finished. I will use the figure in page 8 of the slides to summarize the results we have learned so far. Note that the null space of A and the column space of A transpose are both in Rn. By the fundamental subspaces theorem, the null space of A and the column space of A transpose are orthogonal complements of each other. And if X is in the null space of A, then X satisfies Ax equals the 0 vector. And the vector in the column space of A transpose has the form A transpose Y. And we have the following condition: X transpose times A transpose Y equals 0. where X is in the null space of A, and A transpose Y is in the column space of A transpose. And here Y is arbitrary vector in Rm. Similarly, and recall that the column space of A and the null space of A transpose are both in Rm. And by the fundamental subspaces theorem, the column space of A and the null space of A transpose are orthogonal complements of each other. If Y is in the null space of A transpose, then Y satisfies A transpose Y equals the zero vector. And if a vector is in the column space of A, then the vector has the form Ax. And we have the following condition: Y transpose times Ax equals 0. Here Y is in the null space of A transpose, and Ax is in the column space of A. And in fact, X can be an arbitrary vector in Rn. Now suppose matrix A has rank R, then the dimension of Ra transpose is R, and the dimension of the column space of A is also R. By the rank nullity theorem, we know the dimension of the null space of A is n minus R, because the number of columns of A is n, and we know the dimension of the null space of A transpose is m minus R, because the number of columns of A transpose is m. We also know that Rn is the direct sum of Ra transpose and the null space of A. Hence, the dimension of Rn equals the dimension of Ra transpose plus the dimension of the null space of A. That is, n equals R plus n minus R. Similarly, Rm is the direct sum of the column space of A and the null space of A transpose. And thus, the dimension of Rm equals the dimension of the column space of A plus the dimension of the null space of A transpose. That is, m equals R plus m minus R. This figure is from the book Introduction to Linear Algebra, written by Gilbert Strain. I will use the figure in page 9 of the slides to visualize some of the results we have learned. This figure is from the book written by Gilbert Strain. Recall that Rn is the direct sum of Ra transpose and the null space of A. So every vector x in Rn can be written as the sum of y and z, where y belongs to Ra transpose and the z belongs to the null space of A. Now suppose ay equals b, then we have ax equals ay plus az, which also equals b, because az equals 0, because z is in the null space of A. And know that b is in the column space of A. From this figure, we know that if the dimension of the null space of A transpose is greater than 0, then the mapping Ax is not onto. Because if the dimension of the null space of A transpose is greater than 0, then we can find some non-zero vector B in an A transpose. And for such B, we cannot find a vector X in Rn such that Ax equals B. And thus, in this case, the mapping Ax is not onto. On the other hand, if the dimension of the null space of A is greater than 0, then the mapping Ax is not 1-to-1. Because if the dimension of the null space of A is greater than 0, then there exists some non-zero vector Z, such that X equals Y plus Z. In this case, X and Y are different vectors, because Z is not the zero vector. However, we have Ax equals Ay equals B, and both Ax and Ay mapped to the same vector B, and thus the mapping Ax is not 1-to-1. To summarize, the linear transformation Ax from Rn to Rm is 1-to-1 if and only if the dimension of the null space of A is 0. And the linear transformation Ax from Rn to Rm is onto if and only if the dimension of the null space of A transpose is 0. Next, we discuss example 4. Given a matrix A, our goal is to compute the 4 fundamental subspaces of matrix A. And in section 3.6, we already learned how to compute the 4 fundamental subspaces. If you are not familiar with how to do it, you can revisit section 3.6. After you find the 4 fundamental subspaces, you can perform a solution verification to check whether your solution is correct or not. We can check whether the null space of transpose and the column space of A are orthogonal subspaces or not. If an A transpose and the column space of A are not orthogonal subspaces, then this means you made a mistake during your calculations. In this example, 101 transpose is in the column space of A, and -1, -2, 1 transpose is in the null space of A transpose, and the 2 vectors are orthogonal because their inner product is 0, and this is consistent with the fact that the column space of A and the NA transpose are orthogonal subspaces. Exercise 13 presents some well-known results regarding the fundamental subspaces of A transpose A and the fundamental subspaces of AA transpose. You can use the following hint to prove the 6 statements, and the proofs can be found in the last page of the slides. I have selected some exercises for you to test whether you understand the contents of this section, and the answers of the selected exercises can be found at the end of the textbook and in the next slide. After learning this section, you should be familiar with the concepts of orthogonal subspaces and orthogonal complements. It is better for you to use simple examples in R3 to develop the intuition behind the concepts of orthogonal subspaces and orthogonal complements, rather than directly memorizing the definitions. You should also be familiar with the main results in this section. That is the Fundamental Subspaces Theorem and the Theorem 5.2.3 and Theorem 5.2.4. I hope this video provides you a better understanding of the fundamental subspaces of a matrix. If you have any questions, please do not hesitate to ask.